Hello everyone. In this video we're going to talk about recurrent neural networks or RNN, and we're going to work on a simple recurrent neural networks. And recurrent ones are the ones that have feedback, the ones that a state or the results of a layer can go back to itself or to other layers. Okay, so they are not just a straight fit forward. And because of those delays that you have, and because of those feedbacks that you have, so a delayed version of a signal or a state can go back and be used in other places. Because of these time delays and this feedback, they have a memory. And because they have memory, so they can learn sequences of data like time series, like a speech, like writing that we have in natural language processing. Okay, so they are very, very useful, like when they are used for stock market predictions, where they are used to predict what is the next word in this sentence or anything like that. These RNNs are used big time. So here, as I said, we're going to work with a simple recurrent neural network with the ones that only have a single delay, and it just goes from the hidden layer back to itself. And the simple one is called the L-man network. Sorry, so it has only one time delay in the hidden layer only. And so if you look at the network, it looks like this. You have input, you have output, and you have the hidden layer or state. So h at any point is a function f, and a linear function of some weights times input plus some other weights times the delayed version of that h, right, which is basically this guy. So when this guy comes back, it becomes h of t minus 1. It becomes a delayed version of the signal. Okay, and then some bias. And the nonlinear function here is f, and then you pass that h multiplied by some gain here and some bias, and you pass it to another nonlinear function g, and you get your y. And this is the what we call the unfolded form of this network. You can write it this way. So here you have h of t minus 1, h of t plus 1, as well as x and y at these three instances, let's say, right? So you see that each h is going to be fed into the next h, as well as the x at that time point, right? And then basically the combination of ht minus 1 and xt will form ht, and ht is feed forwarded into yt. So this is the expanded version of L-man network. So one thing is, these equations are recursive, the top equation, right? This top equation in 1 is recursive. And so you need to start at time of t equals 1 here. Then you need h at time 0. And h at time 0, you cannot find it from another one, because if you plug in t of 0, then it means h at negative 1, and we don't have negative time. So here, this h of 0 is going to be a parameter that you have to feed into the system, which many times we do. We consider it 0. Sometimes we don't. We consider it another unknown parameter, like these weights and biases, and we try to what? We try to learn it with steepest descent or any other algorithm, okay? But many times we simply just consider this to be what? 0 for simplicity, and then, of course, the network is going to compensate for that if it's wrong, because if it's h0 is not 0, the network very fast tries to learn and adapt and adjust or catch up for that h of 0 that was not 0, but you forced it to be 0. Now, one thing you see here is, as opposed to hidden Markov models, which I should make a video about it soon, each output at each time does not only depend on the input at that time and the previous input, it also depends on all previous inputs. So if you look at this ht, you might say, well, look, this ht only depends on xt. No. It also depends on xt minus 1. Why? Because xt minus 1 formed ht minus 1, and ht minus 1 is a component for forming yht. And then ht is the one that forms the output. So you see yt is directly related to xt, but also indirectly related to xt minus 1, also xt minus 2. Because xt minus 2 was fed into what? Fed into h of t minus 2, which itself affected ht minus 1, which itself affected ht. So all of these previous x's or h's are going to affect the y's. Okay, so that is one major difference that you have in an RNN and a hidden Markov model, where y of t is only a function of what? A function of, and you might not want to use h, some other letter, w, of only x of t, and maybe x of t minus 1. Okay? Yes, or just x of t. Okay, now going forward, one of the things I want to show you is, so here is an expansion of this network for 2 steps. So here I calculated h of 1 based on this formula, based on h of 0 and x of 1, as you can see. Since h of 0 is a given number, then you see h1 is just a function of x1, y1 is a function of h1, h1 was a function of x1, so y1 is only going to be a function of x1 also. Then h2 is a function of x2 and h1, but h1 was a function of x1, so h2 will be a function of both x1 and x2. y2 is a function of h2, so y2 should also be a function of x1 and x2. And then if you go forward, you see y3 is a function of x1, x2, x3, and in general, yn is a function of all previous x's, from x of 1 all the way to x of n. Okay, so this is the general property of the recurrent neural networks. And let me tell you one thing before I go about the rest of them is these 2 functions f and g, which in general are nonlinear function, if we choose them to be an identity or linear function, what happens? Okay, so they are identity functions. Then you see here y becomes just this linear combination of h and in this case weights w and b, and this h, if I replace it from the formula of f, but again this f is an identity, so it's going to be this interior argument for it. So if I plug that in here and then expand it, you'll see that y of t is going to be some matrix, some gain times x of t, plus some gain times h of t minus 1, plus some constant. And remember, h of t minus 1 is a combination of xt minus 1 and h of t minus 2 and some bias. So if you plug that in here, then y of t will be something times x of t plus something times x of t minus 1. And if you keep doing that, ultimately you see that y at nt, where t here is like a sample time, it is going to be what? Some constant times x at that point, plus some constant times x at the previous points, x at the 2 previous points, all the way to x at the first sample point. And this is what you know as autoregressive linear model, okay? Autoregressive linear model, or in signals, in signal processing, people call it infinite impulse response filter, okay? IIR filter. So if you hear these words, autoregressive linear model or IIR filter, these are a simplified version of a recurrent neural network where f and g are what? Simply the identity functions. And they can do a great job for prediction as long as the data you have is clean, perfect data with no nonlinearity, no noise or anything. And I'll show you that in my TensorFlow code. If you have very good, clean, noise-free data with no nonlinearity, and one form of it is noise, basically, then this autoregressive model can do a very, very great job, okay, in prediction. But when the noise comes in, when those unpredicted variation comes in, actually the IIR or autoregressive can by no means predict the future values, okay? Even a simple recurrent neural network is very limited, and I'll show you that. Okay, it might do a good job for a couple of steps, but after that you start looking at the drift. Okay, now what is one of the major advantages of these recurrent neural networks, other than they have memory? The other advantage they have is they use the same weights and biases for all data points in one layer, so they use a lot fewer, much fewer weights and biases or parameters compared to a dense layer, and so we can train them faster. And you can see that here, right? Regardless of which time point, t minus 1, t plus 1, these weights and biases here, this w of xh, which is from the input to the hidden layer, whh, which is from hidden layer to hidden layer, and bh, the bias of the hidden layer, as well as WO, which is the W of the output layer, and BO, which is bias of the output layer, these guys are going to stay the same for all different time points, for all different values in the time series. So we only need to find these 5 matrices or vectors in general, and you use a lot less, much smaller number of weights and biases or parameters to find. So just like a convolution network, these RNN networks are very efficient. Now, the number of neurons in the hidden layer is a hyperparameter. So this hidden layer, you can have as many neurons as you want. It's a hyperparameter that you can find. The dimension of the input can be any dimension. It doesn't need to be a scalar, okay? It can have as many dimensions as you want. We can call it D. As well as the output. The output can have as many dimensions as you want. You might call it K. And the length of the series that you pass to them is also any, could be any number, so you might call it T, okay, or any other parameter. So you have freedom. They are not limited to only a scalar input, a scalar output, okay, or binary input output, or anything like that. And in general, these recurrent networks, you can have as many hidden layers as you want, with as many neurons as you want, and these delays could be variable, so you don't need to stick only to one delay. You might use n delays, okay? So this delay in general could be d instead of 1. You might have t delays, or 4 delays, or 6 delays, whatever in general, d delays. But in a simple one that we are talking right now, we only have one hidden layer and one single delay. Okay, so recurrent neural networks could be very, very complicated. And in our future videos, we're going to see some more complicated ones. But here, this is like the simplest of all that we want to start with. Okay, so the number of these hidden layers is also, and the number of delays in these layers are also what? Hyperparameters to choose, as I said. Good. Now, we can use these recurrent neural networks to predict the data one step ahead of time, or what? Several steps ahead of time. So for instance, I can look at all the values of the market, right? The index, the stocks market from, let's say, the beginning of last year to, let's say, what? To beginning of December, use those as training data, and then I can only predict the stocks market in the first day of December, or I can predict it from first day of December all the way to, let's say, the 5th day of December. So the number of steps that we want to predict ahead of time is under our control. Typically, the more steps you go forward, the more drift you will gonna see between reality and predictions. And these number of steps, there is a technical term for it, it's called horizon. Okay, so horizon is the number of steps ahead to predict. Now, how would you train a recurrent neural network? That's an interesting thing that we need to see. We use backpropagation for training these, but it's a little bit different. Okay, it's not the same as what we did in the past. This version of backpropagation is called backpropagation through time, and it's just a fancy name. It's just for some small modification you need to do to it, although it looks a little bit scary in the beginning, but it's not really that bad. And I'll tell you why, but it's a little bit different than original ones that I showed you in one of my previous videos. So how can I train an RNN network? So here, you can define a cost function, and it could be as simple as mean squared error, MSE. So what you do is, at each time point, you have the target value for that point and the predicted value for that point. You subtract them, square them, sum them all up, and divide by the total number of what? Time points over which you are doing the predictions. So this T here is the total range that over which you are doing the predictions. Okay, this is not the horizon one here, because this is for training step, not prediction step really. So each one of these square terms, we call it JT, and again, summation of them over the number is the cost function we need to optimize. Optimize with respect to what? With respect to these weights. This one, this one, this one, this one, and this one. And so we need to find the partial derivative of this J with respect to these weights. Now here, I'm just going to show you, if you want to do it with respect to this WXH, which is in the hidden layer, and that's one of the harder ones to calculate, how would you do that? Well, so partial of J with respect to that WXH is going to be 1 over T partial of all of these individual J's with respect to that. So in order to calculate that, we can just look at one of those individual partial derivatives here, okay? Like J1. And J1 is what? Is target number 1 minus Y1 squared, right? Now for Y1, I replace it with what we have from the formulas of the element network. Okay, so here I plug in 1, so it's going to be G of W OT, H1 plus B naught, and H1 itself is F of WX H transpose X of 1 plus WH H transpose H of 0 plus B of H. So I just plug them all in, and so that's what you can see over here. This is your Y1, okay? Now I want to take derivative of this J1 with respect to what? With respect to this WXH. Well, how would you do that? So if I give you that in a calculus class and say, hey, this is my function, this J1 is this function of that parameter, take the partial derivative, what would you do? Well, you start and say, hey, this is a square term, this is u squared. So derivative of u squared is 2u times u prime, yes? So 2u, right? And u prime is the derivative of the interior of that with respect to w. This target is a constant value. It has no derivative with respect to w, so it's the derivative of y. So this guy is the derivative of that y of 1 with respect to that w of xh. And what is that? Well, there is a negative one here, or not that actually, it's the derivative of, it's the derivative of the target 1 minus y1, this whole thing with respect to wxh, right? Because that is u. So derivative of that, this negative 1 will come out, and then it's going to be derivative of y with respect to w. So the first thing we have is negative 2 times u times this partial derivative, right? And that's what you can see here. This first part is negative 2 times u. All of this bracket is that u, okay? Because u is the trace minus y1, and this is trace, and this is y1, okay? So that is basically partial of j1 with respect to y1, and we'll talk about it. Let's not focus on that right now. Then what? As I said, now you have to take partial of y1 with respect to w, and y1 is this guy. So when you want to take derivative of that with respect to w, it's g of u plus b, right? Or b is inside actually. So you can just call it g of u. So derivative of g of u is what? Is g prime of u times u prime. G prime of u is what you can see here. And u prime is the derivative of the interior of g with respect to this weight. Now, interior of that is this guy. This b is constant. This W transpose is the part that is multiplied by f, so that should come out, and you can see it here. And then this is like the derivative of, so it's like this, f of some other u or some other thing. So now you have to take derivative of this one, and derivative of this W O transpose stays, and then you get what? You get f prime of u times u prime. This is that f prime of u, and u prime is the derivative of interior of f, which is this one. And the derivative of this with respect to this w is simply that x1, which you can see here. Okay, so this is a good practice for your calculus class, basically for your chain rule, right? So here we did the whole thing, we expanded it. I deliberately expanded everything so you can see that. Now, let's see. What is each component here? So, this one here is the partial of J1 with respect to Y1. This guy is partial of Y1 with respect to H1. And finally, this one is partial of H1 with respect to WXH. So this, we wrote it as the product of these three terms. And clearly, of course, if you do that, you're going to get this, and that's chain rule. Okay, so we didn't do anything really out of calculus. That's exactly what it is. And it's not bad. I mean, like, you can do that. It's three chain rules. You can do that. What you need is the f prime function and the g prime function, but you can do that. And f and g. So you might say, well, that wasn't hard. That's the same thing that we did for regular neural networks, feed-forward. But now I want with you to raise the bar a little bit more. And this time we want to optimize J2, which is target 2 minus y prediction 2 squared. Take partial of that with respect to the same weight, right? Because we need all of these individual ones here. We need all of these individuals, partial of them with respect to WXH. So that's when you add them and divide by t, that's the partial of j with respect to that weight. So we need J2, J3, J4, all the way to JT. Now look at J2, see what happens with J2. J2 is what? As I said, target 2 minus y2 squared. Target 2 is just a constant. But y2 is what? That's g of h of 2. This is h of 2. And h of 2 is basically what? It's f of, I mean, like that part that b of it is not, this b part of it is not h of 2. This part is h of 2. This guy. That's h of 2. Or, sorry. Yeah, this part here. That is without the w. This is h of 2, which is multiplied by w and added to b. That's h of 2. And h of 2 is a function of x of 2 and h of 1 and bh. Okay, so this guy is h of 2. Good. Now, here, let's plug in what we know. So, what's the problem here? This x2 is a given value. This target 2 is also a given value. The problem here is this guy, h of 1. This h of 1 is not a constant. That guy depends on what? Depends, as we just saw it up here, right? It depends on x of 1, h of 0, and b of it. So that is what? This is your h of 1. So now if you expand it, your J2 will be this. That whole thing. And now this weight WXH does not, like last time, it does not only appear in one place. Now it appears in two places. If you expand J3, you're going to see this weight is going to show up in 3 places. In Jn, it's going to appear in n places. And you have to calculate all of those partial derivatives. Okay, so the more you went into the network and you go into the future, because of this feedback thing and because of that each previous one is affecting the next one and all of these previous ones are affected by these weights are going to show their effect in a lot of places. And so taking these future derivatives is going to be more complicated. Now let's see how we can do that. Okay. Not that scary, but I want to show you why we need a little bit different approach here. So how do I take derivative here? Well, again, this guy is constant. So again, this is a minus u squared. So it's going to be negative 2 times u that you can see times u prime. Now u prime is the derivative of basically that whole thing here. And now it involves the g prime function. And whatever inside the g we have, if you look inside the g, that's this huge f function multiplied by WOT transpose. So that comes here as well. And the whole big function of f, which has another f inside of it. So you see here I have f of f. Now when I want to take derivative of this f of f, what happens? Well, of course you get f prime. Now for this guy, for this first WXH, the coefficient is x2, so it comes out. But for the second part, which is this, now you're looking at what? You're looking at f of this. You're looking at f of that. So this weight WHH comes out, okay, which you can see here, right? And this is the rest of the derivative, okay? And then you have what? Now you want to take the derivative of this inner part, where x1 will come out. And now you have derivative of f of f. And what is derivative of f of f? Well, if you remember, f of g or f of g of u, if you want the derivative of that, what is it? It's from your calculus. It's f prime of g of u times g prime of u times u prime. So we have to use that here, and that is exactly what you can see over here. Okay? This is that g prime. This is that u prime, and this is that f prime of g, all multiplied together. Right? And so now if we want to write all of these huge terms in terms of these smaller partial derivatives, how can we do that? Well, let's take a look. How can we write them in a more general notation so we can use it all the time? Because we cannot always go and expand like this. It takes forever. So is there a nice formula we can pull out of this J2? Well, let's find out. So this top line is definitely, again, partial of J2 with respect to Y2. And then y2 is directly a function of h2, right? You can see it here, that each y is the function of the same h, and j is a function of that y, and that h is a function of what? Previous h's and what? The previous x's. That x will bring its own weight, and that previous h, inside of it, it has this wxh in it. So if I go back, the second part, you see that's partial of y2 with respect to h2. The last part is a little bit different. It's not simply derivative of h1 with respect to that weight. The last part has two components. You see, I added them and put them in a brace. What is the last part? The last part is the same as what we had earlier, derivative of h1 with respect to wxh. This times multiplied by partial of h2 with respect to h1, because h2 is a function of h1, and then this guy here is partial of h2 with respect to wxh. Okay? So h2, as I said, in two places it will have wxh. One directly, h2 will directly have wxh in it. Let's go back here. Let me one more time show you. When I do h2, h2 will have directly wxh in it. And also because it's a function of h1, and h1 is a function of this wxh in it, so you have to what? You have to take partial of h2 with respect to h1 multiplied by partial of h1 with respect to wxh. So we call it the total derivative. Okay, we call it what? We call it a total derivative. So this whole thing, if you want to give it the name, this whole thing here is partial of h2 with respect to wxh, but total. Right? And again, how is it written? It's direct derivative of h2 with respect to xh plus indirect derivative, which is partial of h2 with respect to h1 times partial of h1 with respect to wxh. And this initial term, you can multiply it by a 1. You know, a 1 doesn't hurt to be multiplied. And this 1, if you don't mind, I can call it partial of h2 with respect to h2. Right? That's 1, correct? If I do that, now these two terms on the left and right would look similar. They are all partial of h2 with respect to one of the h's, either the same h or previous h, and multiplied by partial of that h, whatever it is, with respect to the weight. So I can write it like a summation like that. K goes from 1 to 2, partial of h2 with respect to hk times partial of hk with respect to wxh, and this whole thing is multiplied by those two previous partial, j2 with respect to y2, y2 with respect to h2. You see? So in the past, we only had this. Now, instead of that simple thing, we have a summation. So now if I want to do 3, if I want to do partial of, let's say, j3 with respect to wxh, I can use a similar formula and I don't need to do all those expansions. Why? I say this is what? Partial of j3 with respect to y3, because it's directly a function of y3. Partial of y3 with respect to what? h3, because it's directly a function of h3. And then times total derivative of h3 with respect to that wxh. And how is this total calculated? It's the direct derivative of that plus derivative of that h3 with respect to all previous h's. So like H3 with respect to H2, H2 with respect to WXH, H3 with respect to H1, H1 with respect to that, okay? And that whole thing, I can write it as a summation. I can say this is K goes from 1 to 3 partial of H3 with respect to HK times partial of HK with respect to what? WXH. You see? And I can expand it for any arbitrary. So if this guy is not 3, if this guy is n, I can do that as well, right? All I need is make this guy n. Here. You see? So I can write the general format for it. And because here we need to go back and do all of these other partials, instead of just the direct one, we need to take all of these previous H's into consideration. When we look at all the effects of these previous H's as well, we call it what? We call it back propagation through time. So if you want to train your network, you need to first calculate what? All of the H's. All of the H's have to be calculated. Okay, because this guy is what? As I said, this guy is H of 1, right? Or this whole thing, as I said, is what? This guy here is H of 2. So first, you need to calculate all HI's. I goes from what? 1 to T. H0, you can assume it's 0. You have to calculate all of these H's using all of the X's that you have. And once you have all of these hidden layer states or values, now you can go and use this update formula. Okay, so I explained that one for you as well. And here is that formula written for you in a beautiful way. And here, this is the partial of the entire cost function now, which is 1 over t, the partial of the individual j's. And the partial of individual j's is this bracket that I showed you, right? Remember this guy. You can see it inside this bracket. So this is the cost function that you need to what? You need to minimize. Now, there is one problem with minimizing this cost function in equation 3, and that is when the index I goes high and the length of your time series is long, really, the problem becomes that you have a ton of these partials be multiplied together, right? Just imagine this H is H10. So what's going to happen? You're going to get partial of H10 with respect to what? H9 times H9 with respect to WH, but you don't have H9 directly as a function of WXH. So from H9 you have to go back to H8, from H8 you have to go back to H7. So you get a ton of these partials multiplied together. And if they are small terms, because all of these terms are smaller than 1 multiplied together, you get the vanishing gradient problem. And if they are bigger than 1, guess what? Then you get exploding gradients problem. Okay, so you might get very, very large terms, right? So you're going to get what? You're going to get vanishing or sometimes what? Exploding gradient problems. So in practice, we don't go all the way back from the time that you are all the way back to k of 1 and look at the effect of all of those partial derivatives. We'll limit this summation, this interior summation, only to a few terms, not all the way back to k of 1. So we go to what? We go to k of t minus tau, so we only go tau steps back, and from there you go to t, and this tau is what? Another hyperparameter that you can choose. So you only look at some recent terms. You only look at what? The effect of basically tau recent terms. And again, that's a hyperparameter for you to choose. And it's shown that this way, many of these existing problems will go away and you get a better convergence of your RNN network. Okay, now that I explained the theory behind it, it's time to what? It's time to look at some TensorFlow code. So here is a simple RNN demo TensorFlow code that I wrote, and you need matplotlib, you need NumPy, you need Panda, you need TensorFlow, and it seems like I brought Panda in two places. Yeah, sometimes you miss, huh? I guess I copied it twice. Now, there are a series of data that I want to show you, time series. One is the stocks market from S&P 500 from Yahoo News, which you can download from this website. And these are for 252 days in 2023. And in this case, I also want to create a function, a cosine function in this case, cosine of 0.2 times t, and generate a bunch of xy data and then perform RNN on this data, okay? So let's say a signal, a cosine signal that you might get from a function generator or from a sensor or anything. So here I do it on a sensor data, and I also do it on some real life data. If I do it on the sensor data, you're gonna see that the performance is actually really good. So first, you know what? Let's do it on the clean y function and see what happens. So here I import my libraries, and then, you know what? Let me close this, guys. And then I come here, and then I create 300 data points, and I use cosine of 0.2 times those values using NP-arrange. And first, I don't add the noise, so I make it a clean, perfect function with no noise, just a perfect cosine function, and see if my network can estimate this, okay? So here, let's go ahead and generate the data and plot it. There we go. You see, beautiful cosine function. And then I'm going to use this data for training the network. Now, when you want to train it for network, you have to prepare your data. And here I don't want to pass all of my 300 data points to my RNN. I just want to pass it every 10 data points. So I want to break it down into chunks of 10 data points, and using 10 values, I want to predict the 11th value. So what I do here, I use t of 10, and in this case, I only have one dimension for input, so d is 1. And the training data, I start with x and y of mt, okay? And then what? I use a for loop, and I go through what? I go through length of the data cosine, which is 300 minus t, so it's going to go from 0 to 290. And then each time from t to t plus t, those 10 data points, I allocated to to variable x small, and then I add that variable x small, which is a 10 by 1 vector, I appended to the matrix x. Okay, and then I go to what? I go to the 11th value and append that to matrix y. So what's going to happen when you generate this data is x is not going to be a 1D data, it's going to be a matrix of data, and you can see the shape of it. It has 290 rows. In each row you have 10 data points for training. And if you look at the shape of y, y is 290 by 1. Okay, or you might just get rid of that 1, which here I'll tell you how we did, but it's basically a single vector. So each single number in one row of y is the target for the 10 values in x to be able to predict that. So 10 values in each row of x should predict one value in the same row of y. Okay, so I break it like that. And now, before I pass it to my network expects the dimension of the x data to be what? N by t by d, where d is the dimension of it, t is the size of it, the length of it, and n is the number of those. In this case, the number of rows, basically. But here, my x, if you remember, if you do this append, the shape of it is going to be 290 by 10. It is not going to have that extra 1. It's not going to have this d in it. It's just out of here, out of this line, x is going to be 290 by 10. It doesn't have that extra 1. So here I'm using this reshape and -1 to add that artificial 1 to it. On the other hand, this y does not need to have that extra 1. This y only needs to be 290 by nothing. Okay, so this y should not be, in this case, a 2-dimensional. It should be 1-dimensional. But x should really be a 3-dimensional with an extra dimension of 1. And you can see their shapes after modification. Now those are appropriate size for the network. So I create a simple element network, as I told you. You see here I'm using an input layer with the shape of t and 1, because each time I pass t data, 1 row to it. Then I use a simple RNN. In TF Keras layers, there is also one layer called RNN, but that's general RNN. This is simple one. This is the element network. And all you need to pass to it, really, there are a ton of parameters, but what you really need here is the number of neurons. So here I say I want 10 neurons. And finally, you have a dense layer for the prediction, and that dense layer only needs 1 neuron because here the output is a scalar. So here I just use 3 layers, as I said. And you might say, what is the f function? What is the g function, right? Those nonlinear functions. If you want, you can specify them, but if you don't, like I didn't here, the default activation function in a simple RNN is what? Is tangent hyperbolic, not linear function, okay? In dense layers, the default is what? Linear, but in simple RNN, the default is what? Tangent hyperbolic. So I'm good with tangent hyperbolic for here. Or if you want, you can use ReLU or anything. And for my optimizer, I use Adam with a learning rate of 0.01. For loss, I use mean squared error, just like always. And now, how do I split all of this data I have into training and test set? I use first half of my data for training, and I use the other half for what? For validation. If you don't like it, you can simply what? Like use 2/3 of it, or 70% of it, or 80% of it for training, and 80% for what? For validation, okay? And of course, the more validation you use and the less training, you're not going to get a super beautiful curve when you go to the cost function. But here, we just broke it down into half and half. Again, you might just want to break it into what? 70%, 30%, or something, which is quite more common. I use 100 epochs. You see my validation is x from the middle point all the way to end, and y from the middle point to the end. And my training is x from the beginning to the middle and y from beginning to the middle, okay? So here, that my data is good, I'm gonna form the network, and then I'm gonna train the network. And it's rather fast, actually. You see the cost function is going down, and it's doing amazing. Look how small it goes because there is no noise. It's perfect, so you should expect an amazing prediction. And look here, almost goes to 0. Again, your test function is not going to behave as beautiful, but it's not going to go up. The reason for this gap is, again, we use a ton of data for testing. But now that that's the case, here we try to now show how good we are predicting. So here, let me first show you the result, and then I'll I'll explain what to do and what not to do for prediction. So here is a prediction we do, and it's just one step ahead. And if you see, the predicted results and the real targets are perfectly on the top of each other. Okay, perfect. Why is that? Well, two reasons. One, there was no noise in the training data. Second one is, we did the prediction wrong here in this code. Now, what did we do wrong? Let me explain. So here you see, for targets, I'm using the second half of the y, and for validation, these are the ones, the validation predictions. I start with empty, and I start my RNN predict method to get me the predictions, and then I add them one by one to this prediction, and then I compare target versus prediction. Okay, so what do I do? First, I go to the middle of my data point. That's where I want to start reading the x's and pass them to the network. And remember, initially target is full with half of the data in y, predictions are empty. So I say, as long as the length of validation is less than the length of targets, keep going. What would you do? First, get xii. What does that mean? Means go to what? Means go to that row number ii in x, and remember we are starting in the middle. So go to the row that corresponds to the middle of data, read 10 data points, reshape them. Why would you reshape them? Because when you read that middle row, the shape of it is going to be 10 by 1. But this predict method, just like your original network, the shape that it expects should be three-dimensional. It should be like n by t by d, not just what? T by d, or sorry, n by t. So you have to expand that extra dimension of 1, and that's what you do here with this reshape to make it like that. Yes, and you pass it to predict, and predict will give you a value. Now, when it gives you a value, the shape of the value this predict will give you is going to be a 1 by 1. Although it's a scalar, but it has 2 extra dimensions of 1, which you don't want. You don't want in this validation prediction for appending. When you want to append it in this validation prediction, you don't want to append to this empty set. You don't want to add something that has a dimension of 1 and 1. You have to get rid of those 2, 1 and 1, and make it a scalar with no dimensions. So in order to do that, here we are using the 0, 0. This, if you pass to it any number with dimension 1 and 1 and say, hey, give me that guy at 0, 0, it will convert it to a scalar, the same scalar, but no dimension. So now that I get the proper scalar val, I can append it to my predictions. And of course, I need to move to the next row, so I need to increment y by 1. And then when I have all my predictions and targets, I plot them on the top of each other like I did, and it works so beautifully. So you might say, what's the problem? Why did we do it wrong? Well, I'll tell you why. So here, when we reach to the middle of the data, after which is only the test data, we should not have any data really, right? We are done. All of our training is used. So now when we start predicting, we should not have these values in X. We should not have all of that row in X. You see what we are doing here? Although for the second half of data, we should not have any training. We should just use the weights and biases, right? But you see here, what do? I go to that row, read all of the X's, generate a prediction for them, and then add them to the prediction. And then when I need the next value, then what? Then I go and use the data in the next row. So let me show it for you here in a picture. So here is half of the data in X and Y, which we use for training. Now we come here, and we get these 10 values, and then we predict and put it here, right? Now, when I want the next value, remember all of these rows are chunks of your original sine function. So these first 10 are this part, the next 10 are this part, the next 10 are like this part, okay? We broke down the signal into a bunch of chunks. So now when I'm in the middle of the signal here, which is this guy here, I really don't have this data in the red anymore. This data in the red does not exist for me. I'm only trained with this initial half of the data. I only have data up to here, this side. This is for test. This is for train. So now when I get this 11th data point here, what should I do in the next row? When I want to predict its next value, should I go and look at all these x's? No, because I don't have them. So what should I do? Yes, you're right. I should basically now look at this portion of the data. So I should get rid of this last point of these 10 numbers. I should get rid of that. And I should add this newly generated y added to the rest of this row. So my next row should be what? Should be whatever the previous row was, except for this last component, which I get rid of, and that guy should come and sit here. And now using this 10 data, 9 of which I had, 1 of them I predicted, now I should predict the next one. And when I get the next one, again, I should now get rid of 1 data more at the back. I bring this guy in, right? Yes, you see that? And this prediction again sits here, and that last data will be removed, okay? So you use these new predictions as a part of your data set for predicting the next one and the next one. This is the correct way of predicting, not using all this data that you had, because in real world you don't. You only have this portion for the training. You don't have access to the second part. So if I want to do it according to that method, what should I change? Look here. Again, I start with second half of my data for Y target, empty for prediction. I go to the middle row, and what do I do? Again, I say as long as the size of prediction is less than target, do. I do the same thing as last time, get that row, add the extra dimension of 1, get the prediction, convert it to a scalar with no dimension, call it value, and append it to the prediction. But, as I said, I need to get rid of this first value here. Okay, how do I do that? The way I do it is using the roll command. Roll is like a circular shift. You can shift all of the data to the left or what? To the right. So what do I do here? I roll -1, means 1 to the left. Means, hey, whatever data that you have, so like if you have 2, 3, 5, and 8, shift 1 to the left. If you do that, what happens? This 3 comes and sits here, that 5 sits here, this 8 sits here. What happens to 2? Well, it goes back here. It's a circular shift, so it becomes like that. But remember, the goal was to get rid of that 2. So what do? Now, this prediction that I have, I'm going to bring it and sit it in the position of that 2. That is what you can see I have done here. I said x last, -1, which is the last element. Replace it with what? With that value. So this last x is going to keep updated with the new predictions and keep being passed to what? To the prediction method. You see, I'm not going down the row. Last time I was going down the row by this I and xii. But here I'm not going down the row. I'm updating this x last that each time I'm passing to the predict method using a circular shift and getting rid of the last entry, replacing it by the new prediction. So now if I run this, the results are not going to be as beautiful as last time because you have accumulated error here. Okay, your first prediction might not be bad, but now that first prediction has a little bit error, which is going to go into the second prediction. So second prediction will have more error, third one more and more. And so you should see a little bit of shift. Now that shift you don't see a ton here. There is some shift, but you might not see it very well. But I can show you that shift can get very bad if I go back and add the noise. Okay, this is, remember, here is a simple model. And even if these functions that I had in my network here, let's go up. If these functions were not even tangent hyperbolic, I mean, if I used a simple linear function here, and this guy is linear, if I even used a linear function, I would do the same very good results, okay? Because there is no noise or anything, okay? Now, if I add the noise, look what happens. So I come back here, and I add a little bit noise, random noise, with some amplification at the same size as ND, and do it again. So now the beautiful, nice cosine is now going to be a noisy cosine function. Okay? And again, I form my network, I train my network, and now that the network is trained, let's look at the loss function. Okay, you might say, well, that's not bad, but look at this number. Last time it was almost 0, now it's not. So if we go and remember, this is the wrong prediction, but just for curiosity, let's just plot the wrong prediction, wrong one step ahead prediction, see how it does. Okay, although this is not real prediction, it's cheating. But let's see what happens when there is noise. So you see here, it's not bad, okay? Of course, your system will just learn the overall trend. It's not going to learn all the noise, especially with the number of neurons that I used. Okay, so it's not bad, huh? But again, remember, this is the cheating version. Now let's do the real prediction, where we only have half of the data, no more, and do the proper one, where the data is noisy, and see what happens. Here we go. Now if you look, let's go up a little bit. Now it's not as beautiful, okay? If you look at here, these guys are not as beautiful compared to this one. It's a little bit better. You might say still not bad, yes, because my signal noise is not still crazy. And it's not bad, still it's following a good pattern of cosine function. Okay, there are some ups and downs, but it's not bad. You see here, and I used here, how many neurons? You see here, I used 10 neurons. And I used a small learning rate, so it doesn't overshoot. And I used a bunch of epochs. So my prediction is not bad. Even the true prediction, as you can see, even my true prediction is not bad. I can do really good one step ahead of time prediction. I can keep the trend. It's very beautiful, actually. So you see my RNN is working, right, for a noisy cosine function. And then, of course, I can run the model summary, and I can get the layers, model layers, layer 0, layer 1, get weights, and I can see all of the weights and biases of the RNN layer and the dense layer. So this is your train layer that you can use, okay? But now, to make it a little bit more interesting for you, instead of this cosine function, this time I want to do what? I'm going to use a real data from S&P 500. Okay, so I'm going to change my X and Y data, and for that I need this file here, which is called S&P 500 CSV, and so here I have added it, and in this case This file I'm gonna let you download it. Okay, I made the CSV file. I downloaded it from this website and properly formatted it into a CSV. So I'm gonna give you download for this as well as my TensorFlow. But now let's look at this case. Okay, let's do the S&P 500 where the data does not look like a nice cosine trend. Let's look at it. So here is the stock price for S&P 500 in some days in 2023. There is no clear, nice, beautiful function or trend to learn, right? So here, you're trying to fit that function with a tangent hyperbolic with some delay, right? That's what basically what you're trying to do, and that's not an easy task. So here, and these are the data for it, if you want to see that. But one thing you need to do in this case is these data are big. They are like 40 something hundred, 4200, 4700. You don't want to pass them directly to your neural network. So what you need to do is you need to pre-process them. So here from scikit-learn, I bring a standard scalar and I apply them to this data. Okay, and this data has a dimension, extra dimension of 1. So for plotting, I need to get rid of it with the squeeze command so I can see it. This part you don't need to see necessarily, but you see here when I basically use the scalar, my data that I'm going to pass to my network are not going to be 40 something hundred. They are standardized with average of 0 and standard deviation of 1. This data I'll pass to the network. Okay, I'm going to pass this data to the network. Next, I'm going to break it into chunks and use those chunks for training. Now here, this is not really the horizon. This is the length of data for training. And here, you might not just want to look at 10 data before. You just don't want to look at 10 days before you to train the 11th day. Maybe you want to use a lot more days. Maybe you want to look at 30 days before, okay? So you can have a better idea of what you're doing. Maybe 10 data points is not enough for a noisy data like that. So you might want to bump that up. 30 days, 90 days, something, okay? As long as the it's quite a bit less than the total number of data you have, which in this case is 250. So 30 is still reasonable, okay? About an order of magnitude smaller. So I break my data into those chunks. And of course, we don't have this. And here you have neurons. I have 10 neurons. Maybe you need a lot more neurons. So maybe you need 25, maybe you need 30 neurons because the data is very complicated. And you definitely want to have a small learning rate and a bunch of epochs in this case. So hopefully you get better data, right? So let's go ahead and train the model. So here we go. We formed the model. Let's train it. And here you can see that when I plot the cost function actually goes down pretty well, but not the test data. And remember, the test data is, first of all, it's a huge portion of the data, first of all, and second, we use a lot of neurons. So maybe here, you see here, we are going up. This uptrend is not good, okay? If you have a constant trend, it could be due to insufficient number of training data. But when it goes up, you are definitely overfitting. So maybe I need to go back and what? Change the number of my neurons, right? Here, when we go with the neurons, maybe I want to go back to some smaller number of neurons, maybe 50 neurons or something, okay? Or maybe 10 neurons, something more reasonable. So maybe you want to retrain your network. Okay, I did it, and now the gap is smaller, but you see the last time they were on order of 0.1 and up. So here they might look more oscillations, but clearly their magnitude dropped, but still there is an upward trend, okay? There is still an upward trend, so maybe you have to stop it a little bit, fewer epochs, and use fewer neurons. So maybe I don't need, and it seems like there is a ton of oscillations too, But again, remember that your training data is not enough. So I go back to 10, and maybe I just use maybe 50 or 60 epochs, and hopefully it improves the result a little bit. There we go. So you see now it's still going down or kind of plateauing. So that's not bad. Again, you cannot make this gap 0 here. You have to have a lot more training data. And again, you can do the split of the data better. But the goal here is just general learning. Okay, so now we go with that wrong way of doing one step. See what it does for us. And you see it's not bad really. Of course, these are the scaled version of the data, both the target and the prediction. These are not the original ones, but you see that it's not really bad. I mean, like, it kind of goes with the trend. But remember, this is the wrong way of doing it, right? What happens if you do it properly? Let's take a look, see what happens when you do it properly without using the data that does not exist. And you'll see something interesting. Here we go. Okay. Yes, you're not going to get beautiful things. And that is because your network is very simple. You don't have enough training data. I mean, it's not super bad. Sometimes in the beginning, it kind of tries to catch up, but after that, you're going to get big gaps. Okay, so in the beginning of it, with some gap, tries to capture the trend, but you see that you're going to start losing it. So here, this network needs a lot more work. It needs more layers. It needs more neurons. It needs more data, a lot more, so many more days for training, because this kind of data is not something very simple. And if everybody could write a simple element network to predict the price of stock market, that would be basically the end of the big stock companies, right? So again, for a simple cosine function or something with noise, it does a really good job. But once the data follows no specific pattern and there are too many variables, then it's not going to be that easy. So just wanted to show you that I have both versions of the code here for you, for real data and for generated data, and you can run this simple neural network on them. Feel free to change anything you want, and thank you so much for your attention. I'll see you in the next video. Thank you.